on the board. If you'd like me to, quickly review some of the topics from this class, that's also on the table. And it's just kind of generally a question and answer session. So the more you guys put into it, the more you will get out of it in terms of asking questions. So I'll start with the normal boilerplate. So the final examination is going to be on the 27th, I believe. 27th, everybody, right? Yeah. In the same manner as the tests, it will be 24-hour open book format. You will have 24 hours to complete. The test will begin at 9 a.m. the day of the exam and close 24 hours later. Coverage for the exam is going to be the entire course as covered in lecture. So we're not just testing on stuff since test 2, because there's not, test 2 was relatively late in the semester. So anything throughout the course is fair game. You might see recursion, you might see some of the numerical computation stuff. You should be reasonably, you shouldn't have to worry too much about topics like 1 to 4, because it's if you need to review if statements and while loops, I haven't been doing my job. Those should be fresh in your brain. You may wish to review some of the intricacies of the data structures that we covered, but generally speaking, if you're familiar with lists and dictionaries as given, then you should be reasonably well set for the exam. Past that point, you can certainly expect a focus during the exam on material that was covered in the last month. So specifically, the testing and exceptions material is likely to be featured. The classes material will certainly be on there, and that'll be quite prevalent. You can think of the classes material as being, that's going to be your bread and butter on the exam. That's going to be where most of your marks come from if you do well. File I/O, certainly there will be some questions pertaining to file I/O, some questions pertaining to the various file formats. Normally we don't do all of them. We pick 1 or 2 and do it on that. And no, I'm not going to tell you which. You have to study all of them. And date time might come up. It's certainly a less important topic than the other ones. And SQL also probably will come up. We have we do a question on SQL pretty much every exam, so you can expect that to be on there as well. Any questions about, yes?
Is SQL topic 11 right now?
I think so, yeah. Topic 11, that sounds correct. Yeah, topic 11. So, notable by their absence, there will be no exam material pertaining to the, what is it called? Graphics, what's it called? The graphing material. My goodness. Visualization. I can show you that quickly. It's basically just, here's how to graph. There, now be covering that on the exam, nor will we be covering the material on machine learning, as we didn't get to it. If you're really broken up about not getting that material and, you know, sometime when all of your exam studying is finished, you'd like to, you know, go and watch some lectures about that. If you dig through the archive on my YouTube channel, there are previous semesters in which I have been able to cover those topics. So the material is there if you would like to partake of it, but you do not need to for the purposes of grades in this class, not this semester. Make sense? Any other questions? Yes?
How focused will the exam be on file?
I'm not going to say anything more than I've already said about it. Files will certainly be covered on the exam, but I'm not going to indulge in like describing percentages of the exam that's going to be this or that. You can expect it to be a major topic on the exam in the same way that classes are a major topic on the exam. They are certain to be there. Okay? Any other questions? Okay. So, does anybody have an algorithm that you'd like to see implemented? Someone, let's see. Yes.
First, I said like I hear an avenue that you said the exam is 36 hours, if I'm not wrong, like
24.
24.
Yeah.
So that was something that, and could we do a sample of JSON?
JSON? Yeah, we can do a JSON question. Let me write down the topics that people would like to see. So, file IO. JSON. Any other topics? Yes.
Can we go over the checkerboard?
The checkers question.
Or anything with like classes, but that one would be a really good one.
Yeah. Any other topics? Really? Nobody? Nobody wants a review of recursion?
Yeah, I'll just leave it.
You had a topic?
Can we go over inheritance?
Inheritance. Sure. Anybody else have any topics they'd like to see? Yes.
I forget what it's called, but with recursion, when you do memoization.
Oh,
Oh, it's called memoization.
Memoization.
Sure. Anybody else got any topics they'd like to cover? Yes. Dates, time? Anybody else? Is that enough? Yeah? Okay, so. So the checkers question is pretty long. Probably long enough that to cover it here would be a lot. But what I can do is I can cover something kind of like something similarly structured. So So, you guys familiar with a game called Reverse Eye? No? Yeah? Got a nod of the head. So, it's a little bit like the rules are simpler, so it'll be an easier demonstration. So in Reverse Eye, essentially it looks a bit like a checkerboard, but it actually bears a little bit more resemblance to Go. But essentially you have a board and you have white and black stones. The object is to capture as many tiles as possible, but it doesn't have like the complicated rules that Go does with respect to like interior territories. It's just like number of stones that you have at the end of the game. That's like what your score is. The play proceeds by placing stones onto the board. When you place a stone, it has to capture other stones, right? And basically, any stones that are between the stone that you placed and another stone on the board of your color, those get captured by you. So, for example, if white were to play here, this would be captured, right? If black then played here, that would be captured back. If white played here, this would be captured again. If black played here, it would capture these two. You guys understand the game? So this is simpler than checkers because like most of the complexity of checkers has to do with the jumping rules. And I'm sure everybody who attempted the checkers question, you know where the complexity of that is. And, you know, the checkers jumping rules is just like a really, really big if statement that's nested like 6 levels. So this should be a good one. This, we'll do this as a class. We'll do this, and this will hopefully also serve our classes generally examples. All right? So, good. I like this. Class, Reverse Eye. Incidentally, Reverse Eye is one that I've always wanted to do for an exam question, but I've never quite gotten around to it. So, class Reverse Eye. Def, init, takes self. Now, we're fortunate because in Reverse Eye, the board always only has one. It's like chess, or checkers. There's always only one layout, right? So def, or not def, what am I talking about? Self.board is equal to, we'll just do it in lists. Let's do a board of 8, 7, 8. Incidentally, if you want your code to look nice, I highly recommend this technique that I'm using here, which lines up all the commas. Okay. We shall call let's say black is equal to 2, white is equal to 1. Everybody with me so far? Pretty basic, right? We'll also define whose turn it is. So self.turn is equal to, let's say, white goes first, because, you know, the chess rule, right? Let's just make that a string, because who cares? Although I suppose we could do it as a number. Yeah, let's do it as a number. There. Good. me so far? So the structure of the game will follow the same structure as checkers, right? First step is to receive a move, right? Then you verify that the move is legal. Then you implement the move. Then you pass control to the next player, right? So let's break that into steps. So def. Let's just skip the parsing, shall we? Is valid move takes self, and so moves in reverse I are easier than moves in checkers, right? A move in checkers may comprise several jumps, right? In reverse I, all you do is pick a coordinate. It's kind of like battleship, right? So we can just take a row and column, which will be numerically ordered from 0 to 7. Make sense so far? Questions? No? Okay. So we then have a method for making the move, self, row, column. And we have next player. Just take self. And just for the sake of interest, let's also define. Let's just do a string thing so we can print the board out nicely. Not as complicated as the one that we usually give you, which has the lines and all of that. Let's just do one quickly. Yeah. So def string convert self let's say output is equal to empty string for row in self.board, for cell in row, output plus equals, let's see, if cell is equal to 0, we do one thing. If cell is equal to 1, we do another thing. If cell is equal to, I suppose these should be else. Help if happen. Yeah. So output plus equals, our blank space character will be X, capital X. Our white piece will be capital letter O, and our black piece will be 0. Normally, when printed, 0 will have a little dot in it or a slash through it, which visually distinguishes it from this. So there won't be as much of a distinction as perhaps we would like, but you know, it should still register. Question?
No, I was just going to say there's no field that is a
Yes, thank you. Good. Then, once we have iterated through a whole row, output plus equals a new line character. Then, at the end of all that, we return output. Good. So, we can actually test this so far. So let's say game is equal to reverse I. print game. There we go. Python 3. This is review. Sesh. Fine. So there we go. Again, it's not especially pretty, but it does display. Question?
On an exam, would we have to end up coding our own string conversion, or would that kind of be to us? I think the last test.
Yeah, we normally just give you string conversion. The reason for that is that normally it's not necessarily a good demonstration of like a coding skill that we're interested in you displaying, and it really helps to be able to see the thing properly. So, yeah, generally we give that to you. So, good. So let's talk now about the whether or not a move is valid, right? Now, in order for a move to be valid, it needs to perform a capture, right? So in order to determine whether a move is valid, we are going to have to write an algorithm to determine what might be captured by a particular move, right? This is also going to be useful in this guy here. So since the code to determine which stones would be captured is useful both here and here, it makes sense to pull it out into its own function, right? That way it can be used by both of these guys. But in terms of determining a valid move, you have the condition not only does this thing, in addition to needing to capture something, there are two additional conditions. Does anybody want to hazard a guess what those two conditions are? Yes?
I've heard the book before, and I think it has to move to an empty space, and there has to be actual.
Yes. Yeah, so, yeah, there being actual pieces around, that's like, you could bake that into the has to make a capture argument.
I mean, the game must not be equal to n.
Oh, yeah, there might be available space. Yes, good. So, yeah, we haven't really talked about victory conditions, but yeah, that's true. But yeah, the one I was looking for is space must not be occupied, right? Which makes sense. Another one, which is kind of, a little bit on the brainy side, I guess. The piece actually has to fall on the board itself in order to be a valid move, which, you wouldn't think about that in real life, but in programming, that's the type of thing you think about, right? So, we will check to see, is the space occupied? Is the, well, let's say, is the move inside the board, right? Does the move capture? So, I would say, just to go back to your point of there must be an available space on the board, I would say that this is actually embedded in the rule that you have to be moving to an empty space, right? You can't move to an empty space if there are no empty spaces. So, is the move inside the board? Well, that's easy. If row is greater than 7, or row is less than 0, or column is greater than 7, or column is less than row, or less than 0, then return false. Right? Make sense? Just simple bounds check. Now, is the space occupied? So the indexing here becomes interesting, right? We have organized it so that the first thing that, like, if you access any index here, you will be presented with a row, right? So rows are being indexed, the 4 columns, right? So if self.board row column is equal to, or is not equal to 0, return false. Return true. And finally, if the length of self dot captures given row and column is greater than 0, return true. Else, return false. So within this, I am already deciding what I want my return result from this function to look like, right? I've already implicitly decided it. I want the captures method to return a list of all spaces on the board which would be captured by this move, right? So this starts to get a little bit tricky. For this, we need a little bit of math. Yes?
Just explain your, does the move capture again? The length of captures is greater than 0.
Oh, it needs to be in rows. Sorry. Or not rows. It needs to be in parentheses. Oh, there. Sorry. Yeah?
Yeah, but it's, how is it wording there? Like, if the length is greater than 0.
Then at least one was found.
Oh, okay. Okay.
Yeah. Did you have a question?
Colon, dictionary symbol.
Sorry?
Dictionary symbol instead of colon.
Oh, yeah, it is.
Dictionary symbol instead of.
Yeah, but curly braces at the colon.
Oh. Dictionary symbol. Bloody Python people.
You need a colon after else as well.
Yes, thank you. Good. Awesome. So. So, pieces can be captured in 8 directions, right? So, if I have a piece, right? That's a valid capture. If I have 2 pieces of the same color adjacent, that's not a capture. If I have an empty space, that's obviously not a capture, right? So what I need to do, essentially, is I need to check in 8 directions to see if I recognize a particular pattern. That is, the first one I look at has to be the opposite of my color, and I have to eventually hit a piece of my same color. For example, in Reversi, if you had a situation like this, and you put a black piece here, these are not captured. Walls protect you from capture, right? So essentially, the way approach this, I'm going to write one algorithm for checking in a line, and then I'm going to define two variables which tell me the delta after each check that I make, right? Because these are variables, in order to check all 8 directions, I can reuse the same checking code, but I can alter what the step direction is using these variables. Okay? So, good. I might define some helper functions here. So, let's say so at step, this is actually, I think, going to end up being slightly different than the way I just described it. So I'm going to set up two arrays. These arrays will tell me what the delta is at any particular stage in the algorithm. So first, I will start with a y step of 1 and an x step of 0. Then 1, 1, which would be diagonally. Then 0, 1. Then 1, negative 1. Then 0, negative 1. Then negative 1, negative 1, negative 1, 0, and finally negative 1, 1. So it's like one, 0, 1, 1, 0, 1, 0, negative 1, 1, negative 1, 0, etc., etc. Right? Make sense? Kind of like a D&D alignment chart. Good. So, which step? We'll start off with 0, and we will have the captures is an empty list. So now we can do the capture algorithm, right? Temp x is equal to row, temp y is equal to column, while self.board at temp x plus x step, which step? And I know that's getting complicated already. Right? While that is equal to a 1, and, well, equal to the opposite of what we are. So, if self.turn equals 1, looking for 2, else? Looking for 1. So, yeah. We'll also need temporary, okay. So, you guys understand what I've done so far? No? A little bit, maybe? So, when we do this algorithm, we have to return to the origin each time, right? I'm eventually going to put all of this inside of a loop, which iterates through which step we're on, right? In fact, why don't we just do that now, since it'll save some hassle. While which step is less than or equal to 7, which step plus equals 1, right? So we're going to go through each of these which steps, right? The steps, basically we're going to go through each one of these combinations, right? That's the purpose here, right? X step at which step is the offset, like the travel amount, given what step we're on, right? We'd simply add that to the temporary, like the temp x, temp y holds our temporary position in the board. That's where we're looking currently, right? So what this is to say is while the next one is a, while the next piece is what we're looking for, we keep looking, right? And we're going to record these guys in another, basically we want to dump all of these positions that we find into a temporary list, because we may have to reject that list completely if we're in a situation like this where the termination condition doesn't turn out, right? And they said, and you said this was easier than checkers.
Yeah.
So, this is still easier than checkers though. So while this is true, we want to do 2 things. We want to update the temporary position, and we want to add any positions found to the list of positions. So temporary captures, put it inside here. Temporary captures is equal to an empty list. Temp captures plus equals, we'll store it as a list of tuples. The X position, come on. Why is my pointer off? Weird. Have I finally broken it? Interesting. Yeah, like I click on this line and I'm clicking. You guys see where my cursor is, right?
Yeah.
Yeah.
What the heck's going on?
Mhm.
Is that touchscreen or no?
No, it's
No, but do you have a touchscreen capability? On your
it's
iPhone?
disabled.
Oh.
Very strange. I'll do it with keyboard. So, 1, I don't know. Maybe I just need to reset my computer. 2, and I see I missed a square brace there. So there we go. We save it, and we say temp x plus equals x step, which step? Temp y plus equals y step, which step? Right? This loop will exit when the next piece along the line we're looking is not what we're looking for. Right? At that point, we have one of two, like a couple of things will happen, right? Well, I guess we also have to check bounds on that. Ah, what a pain. All right. So, while that is true, and, well, all right. If, let's just do, F inbounds. R and C. Return. R is greater than or equal to 0, and R is less than or equal to 7, and C is greater than or equal to 0, and C is less than or equal to 7. Right? While in bounds, I really should just assign to a temporary variable here. There we go. So while it's in bounds, and the self is what we're looking for, then we do that. So we've got two options, right? Either this thing failed because it went out of bounds, or it failed because it hit, our color, or it hit a blank spot. If it hit a blank spot or a wall, then this is not a capture, and we don't keep the recorded captures. If it did hit something of our own color, then we keep it, right? So, if, so let's do the positive condition. So number one must be inbounds. So if inbounds, actually now that the next one is this one, so we're going to have to add this as well. But then you know what? It's really just this is getting ridiculous. I've hit my limit. So now you've seen exactly how much of that it takes for me to declare a variable. Next, x. Next, y. Next, x. Next, y. This should make more sense and is more readable for everyone involved. Next, x. Next, y. Good. So, just to refresh it, we're going to have to recalculate the next one. As well, so next x, next y. Yep, okay. They've got a class in here, so, yeah. I guess that's all we got time for, unfortunately.
Sorry, guys. I guess that's my fault.
Hmm?
That's my fault.
Yeah. All right. If you guys are really nice to me, I might do another review session closer to the exam, so we can pick this up at that point. Okay? All right. All right. Let's get out of here.